And we just spent half of the lecture discussing how two balls will oscillate on one spring. Again, it seems like we spent a lot of energy solving a problem that we already know a solution to. So we are still not convinced that Hamiltonian mechanics is helpful. That's okay, because now we are going to make an intellectual leap from a molecule to a crystal. Rather than having two balls connected by one spring, we are going to have infinity of balls connected by infinity of springs. And that's only going to be still a very simple crystal. Rather than talking about three-dimensional structures, which you all are excited about as material scientists, we will talk about one-dimensional crystal. Let's imagine a chain. So let's imagine a world that is one-dimensional, and it is a world of a crystal. In an equilibrium state, the positions of our atoms in a crystal, they're separated by a lattice constant A, and this is going to be atom number S, so its position is going to be SA. Next atom will be S plus 1. So its position S plus 1A. And the previous one would be S minus 1. So those are equilibrium positions of the atoms in the hypothetical crystal. But what if I take this infinite spring with atoms connected by that spring, those springs, and just give it a little kick? Those different atoms will begin to oscillate, and they will move from their respective equilibrium positions. So I'm going to put my atoms somewhere else. So now this is my system, my 1D crystal. And this is my atom S, and it's displaced from its equilibrium position. And its real position is some XS. And this is my, well, actually it's my S minus 1. And this is my atom S, and this is my atom S plus 1. So this is position XS, this is position S plus 1. So they're all slightly off their equilibrium positions. But they're all connected by bonds. So they're not completely independent. And we have infinity of them. And to make our life slightly less messy, I'm going to define one more variable, which is, well, actually infinity of variables. That will be the displacement of our atom from its equilibrium position. So the equilibrium position for an atom S will be position SA. So A is our lattice constant. But its real position is some XS, which is displaced from that position. I'm going to define displacement of our atom as US equal to XS minus SA. So this will be how far is our atom has gone from its equilibrium position where it doesn't want to go anywhere. Okay, so now that we've got that, let's write energy for this system. So we're again going to write the energy for the system. And the energy for the system is going to be a sum of the kinetic energies for all my atoms plus sum of the potential energies associated with all the springs. And let's be simple and assume that all my bonds have the same bond stiffness. And we're also going to have the same masses for the good measure. The good news is that we're actually going to make a leap to different masses after that. So actually different springs will keep the same masses. So now if we have the same spring constants and the same masses, we can again write our potential energy terms. So the potential energy term will be the difference in positions between the atoms minus the equilibrium bond length. So it will be x s plus 1 minus xs minus a squared, as you guys tell me. So this will be the energy of either of those bonds. But now we have a sum of them. We can write it in terms of displacements. So our kinetic energies stay unaltered, but this thing here I can write differently. I can write it as SS x plus 1 minus s plus 1 multiplied by a minus xs minus sa, right? So this stays, sa goes away, and then you're left with a. So this world holds. But now I can represent it as us plus 1 minus us. So I don't have to drag this a around. So rather than thinking about coordinates, I'm now thinking about the deviations from equilibrium. So here I just basically rewrote this a as s plus 1 a minus sa. That's all I did. Okay, so we have a Hamiltonian. And so this is energy, which means this is also Hamiltonian. And our Hamiltonian is now totally giant and a function of all the different momenta and all the different displacements. So how are we going to find the equations of motion for this? How are we going to find out how our entire multitude of atoms is moving together? We have to solve infinity of Hamilton's equations and come up with infinity of solutions. But that seems very daunting, and we don't have enough time. So instead, I propose that we focus our efforts on solving one unit cell. Let's figure out what's happening to one atom in one unit cell. And then maybe it will give us sufficient intuition to extend it to the rest of them. So let's consider our unit cell S. So, and write a portion of a Hamiltonian that contains everything that pertains to that unit cell. So let's write a Hamiltonian HS, that has everything that describes atom S. So the momentum that describes atom S, the kinetic component will be PS over 2m, that part of the sum of the kinetic energy, plus the parts of the sum that describe the potential energy. So if we think about the atom S, what are the springs that we worry about? Yeah, so the neighbors. So we need to consider both of those components. Let's do that. So we have K over 2. The difference in displacements of our atom S and atom and its right-hand neighbor, plus S US minus 1 and the energy of the spring that connects it to its left-hand neighbor. And otherwise, it's not connected to, that specific atom is not physically connected to anyone else. So we don't need to worry about it. Great, so now we have a much smaller Hamiltonian. So we can now, please.
So for the second part of the position, energy due to position, why is it US minus 1?
Because we have chosen that we essentially always are going to subtract forward.
Okay.
So it's basically we always have this type of terms where S plus 1, we subtract US from S plus 1. So for the S minus 1, this is plus 1. So now back to Hamilton's equations. So we can, our du. So now we can just recall that normally we would write Hamilton's equations as dxs dt, but we can add a constant inside this derivative. So we can write it as d dt as x minus sa, which will be dus dt. So we can write our Hamilton's equations in terms of us, and that's fine. So, but our dx dt was the partial derivative of our momentum, and that is simply ps over m. Our derivative of momentum over time is minus ds d, officially dxs, but again, we can add a constant, something that doesn't change with respect to s, x, and then which means we can write it as dh dus. And then we need to take derivatives of these two components. So here we end up with k us plus 1 minus us. And here we have a minus sign that does not go away. And we end up with minus k us minus 1. Okay? So we have k us plus 1 plus us minus 1 minus 2 us. Okay, so is this okay? Are we on board with does this derivatives actually work? Okay. So the next thing, what we always do when it comes to Hamilton's equations, we are going to take a second derivative of this equation and then substitute this in there. So we get d squared us dt squared is equal 1 over m dps dt, and that's going to be k over m us plus 1 plus us minus 1 minus 2 us. So this is curious. So we ended up with an equation that looked very similar to our system, let's say, of 2 balls on a spring, or 1 ball connected by a spring to a wall. It looks oscillatory, so we have a second derivative of our displacement here. We have a linear term on the other side with a minus sign. This k over m looks like should be some sort of frequency squared, but we have these 2 guys sitting here. This displacement is not independent from the displacement of neighbors, because we now have all those atoms connected. But since we think we are going to have some sort of oscillation, we can guess the solution for this equation. Well, we'll know that we are going to wiggle. So let's look for a solution to this equation in the form that oscillates. So the form that we are going to use is us, we'll call it some vs multiplied by I omega t. And I'm not going to drag the complex conjugate, even though it should be here, but it's going to make our derivations just absolutely enormous if I do. So just we'll consider it just for this oscillatory component. And this omega, we don't know what it is. It's not necessarily this k over m, because this is not a real oscillator equation. We know that it has units of frequency because we're dealing with the oscillation in time, but we don't necessarily know what that is. So this is so we have some mysterious frequency. But now we can take this and substitute it into this equation and see what comes out. When we take a second derivative of this function, and this amplitude Vs here does not depend on frequency, but it does depend on this number, which means here we will have Vs plus 1, here we will have Vs minus 1. So Us plus 1 will be simply Vs plus 1 e to the I omega t, and Us minus 1 will be Vs minus 1 e to the I omega t. So if we substitute our guesses about the form of this solution into the equation, what we are going to end up with will be the first derivative, and a second derivative of u of s, which will give us what? Second derivative of Vs multiplied by an exponential minus omega squared Vs e to the I omega t equal to k over m V s plus 1 plus V s minus 1 minus 2 Vs e to the I omega t. Here can get rid of this omega t's and end up with the equation that looks like this. Did our life get any better? It got a little bit better. And the way it got better is that we now don't have a time dependence. We took that out. But we still have a dependence of this amplitude on each other. But I would like you to look at this function here. We have a dependence. We have this interaction between the amplitude between neighboring atoms that is very similar to something. What do you think this expression is? If I gave you a list of numbers, numbered, so each of those, and it's a list of numbers, and each number in the list has sort of a listing number associated with it. So it's a table. So if I gave you this table, and I told you, do this operation to this table, what is this physically?
I'm guessing like in terms of like smaller scale, it'd be like bond energies or something like that.
I'm thinking mathematically. What does this expression describe mathematically?
The total displacement, like in the middle.
I would like you to think like a computer. This is my axis. Computers do not think in continuous things. Computers think in discrete. And this is my discrete axis of I plus 1, I plus 2. And this is going to be my VI, and then V, I plus 1, and so on. I can connect them all to a line forming a function. And now I ask a computer who's given this information to take a derivative of this V function. How the computer takes the derivative? Computer takes your function, breaks it up into breaks your x-axis into a little delta x's, and then to find the derivative, let's say dv dx, instead what it's going to do at the position s is going to do v s plus 1 minus vs divided by delta x. That's what computer is going to do if it wants to take a derivative. Now computer wants to take a second derivative. What it's going to do? It's going to take the first derivative, subtract the neighboring first derivative, and divide it by delta x. So we'll get v s plus 1 minus v of s over delta x minus vs minus vs minus 1 delta x, all divided by delta x. Looks familiar? Okay, so what you see here is nothing but the second derivative on a discrete plane, on a discrete axis, sorry. And why are we surprised that it's discrete? We're dealing with a crystal. I gave you that axis. I gave you the axis of those discrete positions where your atoms are normally occupying. And now we're looking at how they're displaced from those discrete positions. So of course your dependence on position is discrete because you're dealing with lattice. So what you're seeing here is a second derivative with respect to s, the position. And that second derivative is now again is equal to something linear. So what you're seeing here is an oscillator equation. Except now this oscillator equation is not in time, but in space. So periodicity you're looking at is not periodicity of how something oscillates in time, but how something changes in space. it tells you how those displacements, so you have some amount of displacements in this portion of the crystal. They all progressively change. And then all of a sudden you get the same type of displacements of your atoms after a certain wavelength. That's how wave goes through the crystal. So because this is a second derivative, so this is an oscillator equation, again, we're going to look for its solution also in an oscillatory form, except our oscillatory form will now not be in time, it will be in S. I'm proposing that our Vs will be some sort of U naught e to the I k SA. So SA is my discrete variable for space. And k, little k, is going to be the analog of omega, but in space. So if this is in nanometers, what units is this? Inverse nanometers. So we have inverse length. And what's measured in inverse length? Wave vector, reciprocal space, wave vector space. And wave vector can be written as inversely proportional to wavelength. Okay, now we take this, substitute it into our equation, and see what comes out in terms of k. So we have minus omega squared u naught e to the I k S A is equal to k over m. Now we have v that is s plus 1. So we have u naught e to the k s plus 1 a plus u naught e to the I k s minus 1 a. This is this term here, and minus 2 u naught e to the I k s a. We can get rid of this, get rid of this, get rid of this, get rid of this, 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 all of this. And what we end up with is I'm going to move this minus sign to this side to make my life slightly better. So I have omega squared, I have minus k over m, I have e to the I k a plus e to the minus I k a. I think, no, I'm not missing anything so far. Okay? And what is this here? 2 cosines. Great, so this is our 2 cosines k a. So we can write it in terms of 2k, big K, don't confuse, over m, and 1 minus cosine little k a. And now anybody is really excited about high school trigonometry? Does anybody remember another way of expressing this that's shorter? 2 sine squared. So we have 4k over m sine squared ka over 2. So all this work, what did we learn? I'm going to draw you a picture what we learned. What we learned is that our frequency of oscillation in time for our atoms is equal to square root of 4k over m, absolute value of sine ka over 2, where little k is the oscillation, is the wave vector describing oscillation in space. We can plot it. Our omega versus k plot. It's periodic, right? So it's going to be 0, it's 0, and then it's going to do this. So I'm only going to plot it in its first period, from minus pi over a to pi over a. So our frequency of oscillation of our atoms in time depends on how those collective oscillations are going to change in space, how they're going to propagate in space. That relationship between omega and k is referred to as dispersion relation. That fact that your omega is a function of k Does anybody remember encountering this type of relationship in your electromagnetics class? Does anybody remember what that is for a different kind of wave? Electromagnetic wave, light. Does anybody remember what it is for light? What is this relationship between k vector for light and the frequency of light? For light, it was very simple. For light, your relationship between frequency and wave vector was linear. That was for electromagnetic wave. The wave that we talked about today was a wave of oscillations, of atoms being displaced from their natural positions. What wave is that? Pressure wave. What is a pressure wave? What is the other way to call it? Sound. What we learned about today is sound. More about it on Monday.